Hey, hello. Looks like 121 students. Looks like we got a little mechanics one with a object going down an incline. So I was asked if I could help out with this one, and I thought it might be good to make a video for everyone. Even though I think most of you have probably finished up on this section here. But I'll run through it here. It says a box is sliding down a ramp which is inclined at an angle of 45 degrees. All right, so it looks like this was one of your homework or quiz questions. So your numbers might be a little bit different, but I'm going to put here then 45 degrees. So a box is sliding down a ramp that is inclined at an angle of 45 degrees. The coefficient of kinetic friction between the box and the ramp is 0.25. The acceleration of the block down the ramp is blank meters per second squared. Okay, so we're going to have a block, and let me use this as an opportunity to kind of go through what I think is the best way to approach these Newton's laws of motion. And there are 4 steps, okay? So step number 1 is get a good physical picture of what and why things are going on. Number 2, draw the free body diagram. And I like to say that the second step then is easy to do if you did the first one well. Then the third step is, again, easy to do if you've done the second one well, and that is you can write out the equation. So you can use Newton's 3 laws, but particularly the second law, and then figure out what the equations are, and then finally you can solve those. And so these are the 4 main steps that I always like to recommend. And starting with the idea that, well, I'll just go through it. Number 1, you got a good physical picture of what's going on. So here's what we have is we have a block. Now, the block really is being pulled by gravity straight down. So I'll call that mg, its weight. But as you can kind of hopefully see on a slippery slope, if you will, there would be a component of this force down the hill. And so what pulls it down the hill is not the full force of gravity, but a component of that. And so this thing wants to go down the hill. But of course, there is also, maybe a little different color here, there's some rubbing going on here. And so that's the friction that is keeping it from going down the hill. So I'll put a little arrow and saying there's a force going up the hill. And so that's the step 1. You got a good physical picture of what's going on. And if the answer to that is yes, let's move on to step 2, which is then the free body diagram. And so here's the object, and in a free body diagram, the idea is to draw only the object, and then draw with arrowheads the forces, because we don't really care what the force is. We don't care if it's a gravitational force or a frictional force or a spring force, whatever, just there is a force. And so we want to put that in our diagram. So I'll do our forces in green. And so here is the gravitational force. And I kind of mentioned it just trying to get an understanding of what was going on. And then I like to say everything in contact with it. And of course, a big thing in contact is, we said, this rubbing. That would be the frictional force. I'll put a little F and I'll put a little K because it seems to imply that it's kinetic. We could question that, whether it's sliding or not, but given the nature of the question, I think we have to say that it is sliding and there is kinetic friction, not static friction here. The other thing, though, is that the incline would be pushing perpendicular to the surface. You might even argue here that this normal force and the friction are really one force. Maybe I'll do a different color and say these two together, dot, or, something like this. In other words, the surface is really the only thing touching it. So you might argue that there's only really 2 forces. One is the force of gravity and one is the contact. that the incline is making with the block. And so that's true, but we could take this one force and break it down into how much is along the direction it travels, or really opposite to the direction it travels, because it does go down the hill, and the other one perpendicular. So this is our contact force, these two together. These are the components of it, and then this is the gravitational force. Now, that's why I want to put this in a different color. In fact, maybe I'll just cross it out, because it almost looks like that's another force in there. Okay, so that's why I was saying step number 2 is draw the free body diagram. It usually is a little easier once you understand what was going on. And so once I understand the problem, I begin to see there really only be 2 forces, although one of them I'll write as its components. And so the 2 forces would be the force of gravity, and the only thing touching it is the inclined surface, which we break down into a part that is normal to the surface and tangential to the surface, so frictional and normal. Then we get really to kind of the meat of the problem here, and that is, okay, write out the equations and eventually solve the equations. Now, when I say write out the equations, of course, we've learned that we have to put x's with x's and y's with y's, so we need a grid. We need a coordinate system. And I don't know how many of my other videos you saw and how many I've actually emphasized in the video, but usually the best grid is a grid where one of your axes is actually the direction of the acceleration. So I'm going to step away from the traditional, horizontal and vertical grid, but that would work, and move to a grid that is twisted so it goes down the hill. Because we know it goes down the hill, and that's the direction of the acceleration. And here is that advantage, is once you know, and if you know, I got to admit, some problems you don't know the direction of the acceleration, so it's not that easy to say, hey, put the grid in the direction of the acceleration. But if you do know that direction, then putting my x-axis that way, what we'll see here is that what we would call the acceleration in the x direction would be the complete acceleration. So there'd only be an a. You don't have to write it as an a sub x. And then perpendicular, the acceleration would be 0. And so remember, solving the equation means add up all the forces and set it equal to ma. And since we're doing that in the x direction and the y direction, if you have set it up so that one of your axes is along the direction it accelerates, like in this case it goes down the hill, I can just say over here this would be ma, and there's no reason to call it a sub x anymore because this is the whole acceleration. And of course that's what you're asked to find. If I didn't tilt my axis, I would have an a sub x and an a sub y, and then before I can finish, I would have to put the components together to get the total a. And it would work. So again, a grid that would be your traditional horizontal x and horizontal y would work. It just wouldn't be quite as easy. So that's the advantage on this half of our work. But there's also an advantage on the other half of our work, and that is over here, the acceleration in the y direction would be 0, and it's great to have equations that equal to 0. They tend to be easier to solve when you feed them back into a 2-equation kind of a, what in math class you'd call a system of equations. All right, so still working on step 3, writing out the equations. And like I said, picking a nice axis, I got the right-hand side of the equation. Let's go to the left-hand side. Now for here, you'll see that one of the unfortunate things about twisting my axis is now this force of gravity can be thought of as part of it down the hill and part of it perpendicular to the hill. So that is part of it in the x direction and part of it is the y direction. So that's the negative side of twisting your axis. But trust me, even though that's the negative side, there are so many more positive that it's worth it. So what I need to do is to say, well, okay, how much did I twist my axis? And maybe you could see it better in this picture. I would twist my x-axis down so that it matches the incline, which is 45 degrees. So what I've really done is twist everything 45 degrees. So that means if I just kind of looked at a traditional horizontal and realized I twisted it the angle of the incline, let me just write that as theta. That means this inside of my triangle here, this would be 90 minus theta, but let me call that one theta because that's typically then how we label it. We usually label then the piece down the x-axis would be the hypotenuse, and then opposite of theta. So the amount of gravity going down the hill would be mg sine theta, where theta is the slope of the hill, because again, when we tilt it, that makes that angle theta, which makes that angle theta, and we get the x component because it's opposite of that theta. So this is the hypotenuse, this is the total force, and we want to know that x component. And a little bit, we're going to want to know this component, so it's going to be cosine theta for that one. But that'll be over here on this side of the equation. So I'll wait till I get there. All right, so again, I'll say add up all the forces in the x direction. And like I said, this was the hard one to do. But the easy ones then is once you tilt the axis, then all of the frictional force is in the negative x direction and none of the normal force is in the x direction. So those are the advantage of twisting your axis as well as this side of the equation. And even if I didn't have the advantage of this normal force, I still would say twist your axis, because making the advantage of the right-hand side where this is the full acceleration, not an x or a y component, and this is 0, really dominates anything else that can happen on this side of the equation. So again, to the best of your ability, and most problems, you do know the direction of the acceleration, especially those circular ones you're working on now. This is stuff you did last week, but the circular ones, you know it's towards the center of the circle. Or, well, maybe in that one I should say it a little different. I should say set up your grid so that one is towards the center of the circle, because that component would be the radial acceleration, and the other component would be the tangential acceleration. Yeah, that's probably a better way to say it. But anyways, I'm getting off this problem, and I'm getting to your circular motion. But I will hint towards circular motion. I would set up my grid towards, so one of the axes is towards the center of the circle, so that one of the axes represents a radial acceleration and the other axis represents the tangential acceleration, and that's how we talked about circular motion. All right, well, let me pause there, because if I go any further, I'm going to translate to step 4, which is to solve the equation. So I'm going to keep writing out the equation. Let me jump to this side and then kind of do that same thing. Let me write out all of the equations on the y-axis. And again, the amount of force in the y direction, this gravity has a component, and it's adjacent to that theta. So it would be mg cosine theta, and it would be negative. So that is the component of gravity in the y direction. And then going to the other two, the force of friction doesn't have anything in the y direction, so I'll put a 0. And the normal force is all in the y direction, and it's straight up, and that has to equal to 0. All right, so I think I've completed step 3, which is to write out the equation. And so finally now I can go to step 4, which is now let's solve this equation. And at first it may not look like they feed together, so maybe I will start to solve the x1 here by recognizing that the frictional force is the coefficient of friction times the normal. And when I do that, then I recognize that I will need to do the y-axis to get the normal force. All right, so normal force is a plus mg cosine theta for this case. And by the way, a little warning I always like to give students is there's a tendency for the beginning student to think that the normal force is mg for some reason. And it's not. There's so much that can go on It's only mg in the simplest of cases. And this one, clearly, the normal force does not equal mg. It's mg cosine theta. All right, so now that I know that, I can feed that back into here, and so this becomes mg sine theta minus mu, and then the normal force would be mg cosine theta equals to ma. And luckily, there is an m in every term, so that I get a equals, and I get g sine theta minus mu g cosine theta. And for this problem now we can finish it up, because I believe it's a little hard to read, but I think these are all given. Like the angle is 45 degrees, the coefficient is 0.25, and so this would be 9.8 times the sine of 45 degrees minus 0.25 times 9.8 times cosine of 45 equals A. And grabbing a calculator here, I can go 9.8 multiplied by, well, let me check which mode I'm in. Okay, degrees, good. Okay, so 9.8 times sine of 45 minus 0.25 times 9.8 times cosine 45. And it looks like an answer of 5.20. And I did it in all meters per second squared, so that would be the final units here, meters per second squared. And that's what you would put into the computer system for these numbers. I know that these quizzes, they generate different numbers. So some of you, well, probably all of you, will have different numbers. But that's the incline one. Hope that helps.